Hello students, a very warm welcome. In this lecture, we will be beginning with inorganic chemistry, and the first topic that we will be taking up is periodic properties. In this lecture 1, we will be talking about introduction to periodic table. So we will be introducing you to the periodic table today. So let's get started. Alright, so historically, a lot many deliberations were made in order to organize the elements that were known. Alright, so first one was Lavoisier, right? First honorable mention over here is Lavoisier, and he classified the elements into two categories, right? Metals and non-metals. He said that metals, they are hard but not brittle, and non-metals, they are soft and brittle, right? Metals conduct heat and electricity, right? Non-metals generally won't conduct heat and electricity. Metals have a luster, right? They shine, right? Whereas non-metals generally have no luster. They are sonorous, right? Sonorous means that when you hit them with a hammer, right? When you hit them with something, right? What happens is they produce a sound, right? Non-metals generally didn't show such property, right? They had no sonority in general, right? So, guys, the thing was that some of the metals showed the properties of both metals and non-metals, right? As we found out later, right? So, this Lavoisier, how he categorized very simply into metals and non-metals, right? So, this was not reflective of a lot of properties that these elements showed, right? So, this was discarded, right? Then there was Taubert, right? So what he did was he arranged similar elements in groups of three called triads, right? Groups of three elements called triads, in which the atomic mass of the central element, right, was the arithmetic mean of atomic masses of other two elements, right? Or all the three elements possessed nearly the same atomic masses, right? So it worked, right? It worked for some time. For example, lithium, sodium, potassium, right? If you see, if you add 7 and 39 and you divide by 2, it will be 23, right? Similarly over here, almost they were average, right? Or they were closer by. Okay, so, but the thing was, this triad arrangement wasn't followed by a lot many triads that he introduced over that time, right? So what he did was, for example, hydrogen, lithium and sodium was one triad. So if you add 1 and 23 and divide it by 2, you don't get 7, right? So this is very far off. Similarly this, right? And when later more elements were discovered, it was found out that less and less of these elements followed this triad property, right? This triad pattern, right? I hope you've understood this, guys. I'll move on. Then came Newland, right? What Newland did, right? He arranged it in octaves, right? Octaves means groups of 8. He arranged in groups of 8, right? So he was the first to correlate the chemical properties of the elements with their atomic masses, right? So this was the first major leap, right, that Newland's octave rule or Newland's octave law made in the classification of elements, right? So, according to him, if the elements are arranged in the increasing order of their atomic masses, the 8th element, right, starting from given one is similar in properties to the first one, right? So, this is what he said, right? So, this arrangement is called Newland's law of octave, right? So octave is something similar to, right, what you have Sare Gama Padhanisa, right, in Hindi classical music. It's similar to that, right? So it was derived basically, perhaps thought out from there, right? The idea came from there. So it was like this. He arranged it in groups of 8 and he found out that the first element had showed similar properties to the 8th element, and he arranged this according to their atomic masses, right? But the thing was, this classification worked well in case of lighter elements, right? But there were a lot many anomalous situations when we were testing this Newland's law for heavier elements, right? It failed in case of heavier element and therefore it was discarded. right? I hope you understood. So for all this, it showed, okay, so this followed, right? But when we got to, if you're talking about the modern periodic table, the transition elements, the inner transition element, a lot many of them, the heavier elements, didn't show the same trend, right, which Newland suggested in his law of octave. I hope you've understood this, guys. I'll move on. Then came Mendeleev, right? And Mendeleev, with absolute ingenuity, right, what he did was he arranged the elements according to their atomic masses, right? Newland did that, but again, Mendeleev took the same approach, dug deeper, right? And according to him, the physical and chemical properties, right, he got a holistic approach and he looked at it and he said that the chemical and physical properties of elements are periodic functions of their atomic masses. So they showed periodicity according to their atomic masses, right? So for example, if we are talking about atomic mass, right? So there were a lot many elements that were not known at that time, right? For example, aluminium was known, right? Aluminium was known, but he said that there would be another element, right? There would be other element which is eka aluminium, right, which comes after aluminium, right, in the same group, right? And later it was found, this gallium was found, and he was right, he predicted it, right? He said that the atomic mass of that would be 68 and it was about the same, it came out to be 70, right? Now when it came out to be 70, what the scientist who discovered this element, who found this gallium element, he went back to Mendeleev. He said that no, you said 68, but it's actually coming out to be 70. Mendeleev said that go back and check again, right? And when he got back and checked it again, he said no, you were right, Mendeleev was right, it was actually 68 point something, right? So he predicted it very well. Similarly for density, right, very close numbers, right? Melting point he said low, and we got a low melting point, right? The formula for oxide, right, exactly the same, right? I mean, he was able to tell, right, what will be the valence shell, everything in electrons, and how many will combine and everything, right? Formula for chloride was exactly the same. Similarly for eka silicon, right? So in the same group as silicon, the next element, the eka silicon element, was finally found, right, which was germanium, right? And you can see everything is so close, atomic masses, the density, right, the melting point he said high, right? So this was low, 30.2, this was high, 1231, right? Then oxide, the formulas were exactly the same, the chlorides, the formula were exactly the same. So he made a major leap, Mendeleev, right? And he arranged in order of atomic masses, and this atomic mass periodicity or periodic properties according to arranging it to atomic mass, right? And this was followed for a long time, right? Before, of course, Moseley came and he tested out things, right? And he said that atomic numbers actually showed more of a correlation, of more of a linear pattern than the atomic masses, right? But Mendeleev was very close, and when the elements were actually discovered, it was proved that Mendeleev was right. Okay, not exactly right, but of course atomic masses were found to be less in correlation as compared to atomic numbers, but still he was right up there. All right, so right, in fact he was able to predict that, you know, there, when the elements were not discovered, right, he was able to predict, you know, that there will be some sort of an element coming here, right? He was able to predict that, right? He was able to arrange them in 8 groups, right? So 1 2 3 4 5 6 7 8, he was able to arrange them in that, right? And things moved on from over there. Then, so this is the periodic table, right? This is the modern periodic table that we have, which is arranged according to the atomic numbers, right? So hydrogen has 1 atomic number, lithium has 3, sodium has 11, and so forth, right? So hydrogen is actually placed at 2 positions, right? 1 at 1, right? It behaves as both as a metal and a non-metal. That's a different thing, right? So there are some things that you have to remember. For example, this group, this first group, is called the alkali metal group, right? If you notice how many, so this arrangement, right, this horizontal arrangement, basically the rows, right, are called periods. So this is period 1, this is period 2, this is period 3, right, this is period 4, this is period 5, right, this is period 6, this is period 7, this is not period 8 and 9, guys, right? This fills over here, guys. There was no space over here because we wanted to arrange it in a certain pattern, more organized. We wanted to keep it, so it's just like, you know, we put in a library, right? In a library, when you have too many books of a certain category, what do you do? You compartmentalize it in some other area, right? So what you did was, actually they will be placed over here, right? They will be placed in the 6th and the 7th group respectively, but because there was no space there, so this was lifted and placed over here, and there would be more elements added over here probably, right? So these are what are known. So there are 7 periods, guys. There are 7 periods, right? And how many groups? Groups are the columns, right? So this is group 1, this is group 2, right? This is now group 3, this is group 4, group 5, 6, 7, 8, 9, 10, 11, 12, right? 13, 14, you're getting the number, 15, 16, 17, and 18. So 18 groups are there in total, right? Okay. Now, they were arranged in by their atomic numbers, right? And you might be knowing that atomic numbers are filled according to the law that in the first shell, I'm not talking about the subshell, right? The shells include the subshells, right? You must have studied that before also, right? So it's like it gets filled in the pattern 2, 8, 8, 18, 18, 32. 32, right? So 2, 8, 8, 18, 18, 32, 32, right? So this, so if we are talking about the K shell, this is K, this is L, this is M, this is N, right? This is after that, right? So K, L, M, N, and it goes like that. So it's filled in this order, right? And there is of course space left for more elements to be added in, right? I hope you've understood this, guys. So the known elements and some of the elements, right? Some of the elements that can be added which are close, right? So those can be very well organized in this periodic table, and somewhat if at a certain time, you know, which is very highly improbable, if an element with a very large atomic number comes up, right, it can be placed as an exception and its properties can be, but that will be, the chances of it occurring are very low and very few of them might be found, right? So I hope you've understood. So this is a very organized way of organizing the elements in the that are known to us, right? Okay, so I hope you've understood. So what we have is, we have 7 periods and 18 groups, guys. All right, I'll move on. Next thing, number of elements. If we talk about, right, in the first period there are 2 elements, right? In the second period there are 8 elements, right? 2, 8, 8, 18, 18, 32, 32. In the third period there are again 8 elements. In the fourth period there are again 18, right? In fifth period there are 18 again. In sixth period there are 32. In seventh period there are 32, right? I hope you've understood. This follows simple 2, 8, 8, 18, 18, 32, 32, right? The number of electrons that can be accommodated in the shell. So this is the first shell, second shell, third shell, or you must have read this as K, L, M, N, right? Like that. All right. I hope you've understood that, guys. And I'll move on. So what are the periods called? 7 periods, right? We are talking about the periods still, right? The first period is the very short period, guys. It has only 2 elements, right? Hydrogen and helium, right? Hydrogen and helium, 2 elements, right? Second periods is the first short period, right? It has 8 elements. Third period, right, is the second short period. Fourth period, because it has again has the 8 elements, right? Fourth period has 18 elements and is known as the first long period, right? Fifth period again has 18 elements and it's the second long period. Sixth period has 32 elements, it's the very long period, right? And seventh period, guys, it's not yet complete, right? There is a high probability that much more elements, right, which have the last shell, right, that we are talking about, the last 30-second shell, which can include 32 electrons basically to be filled, right? 32 protons or electrons, we're talking about atomic number, right? That can be over there. So this is the incomplete period, it's not yet complete, right? It's highly probable that more elements will be added there according to the atomic mass. I hope you've understood this, guys, right? Further, periodic table, guys, is classified into representative, transition and inner transition elements, guys. All right, so we've talked about 18 groups, right? The S and P block elements are called representative elements. They are called representative elements. Actually, the term representative is it does not give the full picture. The term representative is used because of the fact that the S and P block elements, they are highly reactive, right? So they are called representative elements, right? And they are placed in groups 1 to 2 and groups 13 to 18, right? So if you move back, right, 13, 14, 15, 16, 17, right, and 18, right? Now, if you talk about these two, the first and the second group, right? The first and the second group, this is first group and this is the second group, right? This is the S block, right? This is the X block, right? And this is basically the P block, right? The final electron goes into the P subshell, right? I hope you've understood this, guys. So this is the S block and this is the P block, right? So these are called the representative elements, right? The first, this group, right, this particular group is the alkali metal group, right? This second group, guys, except for beryllium, these are called alkaline earth metals, right? Both of them you should remember, all of them. For example, in the alkali metal group, the first group, right, you have hydrogen, helium, sodium, potassium, rubidium, cesium, francium, right? In the second group, the alkaline earth metal group, right, beryllium is there, right? The first element is beryllium, but it's not an alkaline earth metal, right? After that, there is magnesium, calcium, strontium, barium and radium, right? This guys, these are the noble gases. The final group of the P block is the noble gases. This is group 18. This is the group 18, right? This is group 18 and they are noble gases: helium, neon, argon, krypton, xenon, radon and organoson, right? These are noble gases, right? This is the 17th group, right? 17th group is again very, very important. It's the halogens. These are halogens, right? Which include chlorine, chlorine, bromine, iodine, astatine and the last one TS, right? I hope you've understood this, guys. So these are halogens, right? Apart from that, the oxygen group also you must remember at least some of them, right? For example, oxygen, sulfur, selenium, right? Perhaps tellurium, polonium you can also remember. These are radioactive, right? Oxygen, sulfur, and selenium are non-metals, right? And tellurium, polonium are metalloids, right? Livermorium, you don't have to remember that, right? Generally don't have to remember that, right? The carbon group you can remember, right? Carbon group is very, very important. So first element carbon, then silicon, then germanium, right? Then tin, right? Tin has atomic number 50, right? Tin and antimony, right? Tin and antimony are Sn and Sb are placed in, they are in the same period and they are placed side by side, right? They are in the fifth period and they are placed side by side. All right. After that, in the carbon group, there is also lead. There is also lead, right? there's also lead, and it's called a post transition metal, right? We'll talk about transition elements next, right? Okay, then so in the nitrogen family you have nitrogen, phosphorus, arsenic, antimony, bismuth, right? You can remember this. So nitrogen family, nitrogen, phosphorus, arsenic, antimony, and bismuth, right? Oxygen family, oxygen, sulfur, selenium, tellurium, polonium, right? Tellurium, polonium, you can remember it, right? Okay. Halogens, fluorine, chlorine, bromine, iodine, astatine, and then TS, you don't have to remember that, right? Then in the boron family is again very important. You can very easily remember boron and aluminium, right? And then we talked about Eka aluminium, if you remember, right? Eka aluminium was gallium, right? And then there is indium, thallium, right? I hope you understood this. NH, you don't have to remember them in that case, right? After that, right, let's talk about the transition elements, guys, right? I hope you've understood this, right? We've talked about this portion, the P block and the S block. Now let's talk about the D block. Block is basically what's the transition elements, right? So D block means that the final electron, or the final, I mean the final electron, in fact, goes into the D subshell. Like over here, the final electron was going into the S subshell. In over here, the final electron was going into the P subshell. Here, over here, the final electron goes into the D subshell, right? So you might be knowing, guys, that when we are writing electronic, I mean, if you're writing the available orbitals, right? They are 1s, 2s, 2p, 3s, 3d, right? 3p, like this, right? So the first available d orbital is the third one, right? 1 and 2, there is no such available, right? So that is why it starts from this, right? Group 3 to group 12, right? I hope you've understood this, guys. So this is the D block, and they are called transition elements, right? They are called transition elements because they act, their properties are a transition between the S and P block elements, right, and the F block elements. So their properties lie somewhere in the transitional phase, somewhere in between, right? So hence they are called D block transition elements, right? I hope you've understood this, guys. So we are talking about group 3 to 12. All right, let's go to group 3 and 12, 3 to 12, right? So group 3, guys, group 3 is over here, right? This is the this is scandium yttrium, right? Very important, right? So this is group 3, right? This is 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And then there is a 13th group, right? Scandium, titanium, right? Vanadium, chromium, manganese, iron, cobalt, right? These come in groups 3 to 12, right? This is in the 4th period, and this in the D block, right? So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So you can remember a lot many of them, right? This group, guys, this is the group, this is group 3, right? Scandium and yttrium, guys, if you see, they are over here, but after that this star and double star are made, and this is the lanthanide series, right? Lanthanide series, and this is the actinide series. Guys, one thing that you must know from starting, that this lanthanum, right? Lanthanum is not included in the lanthanide series. I mean, when we are talking about the properties of lanthanide series, this lanthanum is not included because the valential configuration of this is slightly different, right? The electronic configuration of this is slightly different than all this, right? So it's not, I mean, it's the part of the same period. So basically this should ideally be showing the same periodic properties, but this is lanthanum shows different set of properties than the other lanthanide series elements, right? And we'll talk about the electronic configuration of lanthanide series and how it's different from the others, right? This is actinide series. It starts from 89 actinium and goes till lawrencium, which is 103, right? Lanthanide series start from lanthanum and goes till deuterium, right? But if you're talking about properties, right, this is 58 to 32 from cerium to deuterium, right? So this is basically the lanthanide series and the actinide series. Okay, so you can remember that. So this is group 3A, basically this is group 3B, right? And now if you talk about group 4, right? So first of all, in group 3, you must remember scandium, yttrium, and then the lactinide and the actinide series, right? So that is group 3. If you're talking about group 4, titanium, zirconium, hafnium, rutherfordium, right? Then vanadium, niobium, tantalum, right? In group 5, right? So group 5 is actually not that important. Vanadium is important. Group number 23. In fact, till 36, you should be absolutely, it should be at your fingertips, right? And then you can remember group wise, right? For example, the boron family I showed you, carbon family, nitrogen, oxygen, the halogens, right? And then over here the alkali metals, alkaline earth metals, right? Over here we're talking about transition elements. You can remember this, right? If you look at this, just put it on the wall of your room, right? And keep looking at it, you'll be able to remember, right? So if we move to group 6, right? Chromium, guys, chromium is 24. Below chromium is molybdenum and tungsten. Tungsten is important, right? Atomic number 74, it's in group 6, below molybdenum. Below chromium, molybdenum, then tungsten, right? So till here. So basically you'll have to remember till here, right? This portion you'll have to definitely try to remember, right? For example, then there is manganese. Manganese is lot many times asked. Technetium is never asked, rhenium is never asked, right? Then iron, ruthenium, osmium, right? These three you must remember, right? That they come in one group. Then group 9, cobalt, important, right? Certain properties it shows that it is very important, right? Rhodium, iridium, right? Nickel, palladium, platinum, right? Platinum is very important. Palladium and platinum is very important, right? So guys, if you notice, if you go down the group, right? So this is, it increased by 2, then it increased by 8, right? I hope you've understood, guys, right? Then it increased by 8 again, then it increased by 18, then it increased by 18, right? Then it increased by 32, right? So this is how it's happening, right? If you go down each period, 2, 8, 8, 18, 18, 32, right? So you can remember actually the atomic numbers as well. And once you remember the atomic number and you have a good grasp on atomic structure and how the periods and the subshells are basically, the subshells are filled according to the energy, right? According to the energy, if you're talking about filling, right? So first one that gets filled is Ns, right? It has the lowest energy, right? If you're talking about energy, Ns has the lowest energy, right? Nth s orbital we're talking about. Then n minus 2f, right? Then we have what? Right. Then we have n minus 1d. The number we are talking about. If the nth orbital is this will be n minus 2f. We'll have, right? Then this, and then np. This is in the order of energy. So this is how it gets filled, right? Okay, I hope you've understood this, guys. Tungsten is very important over here. Iridium can be asked, right? Palladium, platinum, very important, right? And this from 21 to 30 is definitely important, right? After that, niobium, molybdenum, in fact, zirconium is also important, right? Very important, right? These three, copper, silver and gold, right? 29, 47, 79, right? Atomic numbers we are talking about. This is very important. Copper, silver and gold, right? So they are in the same group. And how you can remember this, guys? That copper, silver, right? 29, 47, right? And gold, guys, which is 79, right? They are in the same group. The group is group 11, right? They are in the same group 11, right? And they are called coinage metals. They are called coinage metals, right? So these coinage metals are in fact in the same group, right? Then zinc and mercury are in the same group, right? Zinc and mercury are in the same group and they show the same property, guys. All right, because they're, I mean, in the, if you go down the group, they will actually show similar properties. The properties will change, right? Of course, if you go down the group, if you go horizontally in a table, in the period from left to right, the property will change. If you do go down the group, the properties will change, right? But they will show a trend, right? So if you're talking about the valence shell configuration, right? For example, if you're talking about copper, guys, copper, if you write the valence shell configuration, guys, it will be 4s1 3d10, guys, right? So this is an exception, right? If you might remember, half filled and full filled orbitals are very, very favorable, right? They have the lowest possible energies, right? So 4s1 becomes half filled when there is an opportunity for 3d to get fully filled, right? So 4s1 3d becomes the electronic configuration of this, right? So copper is like this, right? If you're talking about silver, guys, silver becomes 5s1 3d10, right? So if you remember, you can just remember the electronic configurations also, right? And then if you're talking about gold, guys, it becomes 6s1 and 3d10, right? So this is copper, this is silver, and this is gold, right? Similarly, if you know for zinc, guys, if you know for zinc, which is 4s2 3d10, right, the final shell configuration, you can figure it out for cadmium, right? So cadmium would be 5s2, right? And then it would be 5 4d10, right? Talking about these lactanides and actinides, guys, lanthanides and actinides, the thing is, over here the f orbitals are getting filled, right? That's why they are called the f block elements, right? The lanthanide actinide series are the f block elements, right? They are the inner transition elements, basically, which we are getting to next, but you must understand till over here. So guys, these are the few elements that you must remember. Of course, over here you don't have to remember anything, right? But this much definitely you should remember, right? And then if we come to the f block elements, guys, the f block elements, guys, are lanthanides 4f and actinides 5f, right? So 4f and 5f, guys. So f orbitals can hold a maximum of 14 electrons, right? You know this, guys. So we know that s can hold 2 electrons max, right? P can hold 6 electrons max, D can hold 10 electrons max, and F can hold 14 electrons max, right? So these lanthanides and actinides series, right, guys? So these are the F block elements, and you can remember the F block elements as well, right? If you're talking about the lanthanide series, right, this is in the F block. The lanthanum does not get filled. Its F orbital does not get filled, right? The final electron going is not into the F orbital, right? We'll talk about that later. So it's not sometime classified as a lanthanide itself, right? So lanthanide series is generally starting from 58 to 71. That is cerium to deuterium, right? And then this is actinide series from 89 to 103, guys. So this is important, right? So these are the inner transition elements, or the F block elements, right? F block elements means that the final electron is getting filled in the F block. All right. So guys, the periods, now if I talk about periods, guys, so we've talked about the groups in detail, right? S and P block, the D block, which are the transition elements, and the inner transition elements, or the F block, right? We've covered the entire periodic table, right? Please remember at least till 36 you have to remember at any cost. Then there are certain elements that I've talked about, for example, molybdenum, right? Then there is palladium, right? Then of course the coinage metals in this group: copper, silver, gold, very, very important. Cadmium, mercury, which come below zinc, very, very important, right? Perhaps coppernicum also you can remember, right? Apart from that, tungsten is very important, which comes below chromium and molybdenum, right? Molybdenum and tungsten are very, very important, which come below chromium, right? In the same group as chromium, right? Palladium, platinum is important, which come below in the same group as nickel, right? This is very, very important. The lanthanide series, the first element and the last elements, perhaps if you can remember, right, the elements in this, it will be good. In the actinide series, actinium, thorium is important. Uranium comes in the actinide series. The atomic number is 92, right? This is important, right? So I'll just mark it over here, uranium, right? And then, right, lawrencium which is the final element over here, and deuterium which is the final element over here. These are important, guys, right? If you remember them, it's great, right? Of course, the alkali metals and the alkaline earth metals are very, very important. This is not very important, guys, right? Apart from that, if we talk about the periods, right? So the periods are defined by the final shell, I mean the final shell that is getting filled. And in every shell, if there is a final shell, guys, it's the s orbital that gets filled, right? So for example, the shell that gets filled over here is 1s, right? So this is 1s1 hydrogen, right? The shell that gets filled over here after that, right, this is 1s1 and 2s 1s2 2s1, right? 1s2 2s1, this lithium, right? Similarly, sodium is 3s1, right? This potassium is 3 4s1, right? Then 5s1. So this is the first period, this is the second period, right? If we talk about these p block elements over here, right? So helium is definitely an exception, because this gives this only the second subshell, which is the 2s2, that 1s2 gets that gets filled, right? There is no follow up second orbital, right? So this helium is definitely an exception over here. But if you're talking about this, right, this is 2p6, right? This is, so the p uh, it's is still the second one, right? It's still the second one. I mean, the first orbital that will definitely get filled over here. If you talk about neon also, right? Anything, right? Over here, right? In this second period, if for example I'm talking about, right? It will be 1s2, 2s2 until 2p, right? From 1 to 6, right? If you're talking about the second period, right? Similarly, if you're talking about the third period, the final uh, I mean the final shell that will get filled is the third shell, right? So that's why this is the third period, right? The final shell that is getting filled is the third period. I mean, you won't get, for example, in the third period a 4s1 or a 4s2, right? So you might get a 3p or a you might get a 3p, right? But you won't get something like that, right? And then for example, if you move on to 4s, then you will, what you'll get is you'll get 3d, right? You'll get 3p, right? You'll get 3d and you'll get 4p, right? If you move to the fourth shell, right? So I hope you remember what the periods are basically defined. I'll just repeat it what I said, guys. It's defined as the final orbit, right? Not the orbital, the final orbit that gets filled, right? Over here, the final shell that gets filled. Over here, the first shell gets filled, the second shell gets filled in the second period, in the third period, the second shell gets filled, right? So I hope you've understood this, guys, right? I'll move on. We've talked about this, right? Everything. Now, certain things, guys. Group 1 is alkali metals, right? Group 2 is alkaline earth metals. Beryllium is not included, right? Group 15, which is the nitrogen family, is the are called the pnictogens. Guys, they're called pnictogens, right? Group 16, which is the which family? The oxygen family, guys. It's called chalcogens, right? Please remember, group 16 is not carbon group, it's the oxygen group, right? So these are chalcogens. Group 17 are halogens, you've talked about that. Group 18 are noble gases, right? Group 3, guys, and the lanthanoids, right? The lanthanides, not noids, the lanthanides, guys, are the rare earth metals. So group 3 and the lanthanides are the, so basically group 3a and 3b, right? They are the rare earth metals, right? I hope you've understood this, guys, right? I'll move on. Next up, what I'll talk about is lanthanides or actinides, right? Lanthanides or lanthanoids or rare metals, right? This is not the heading, guys. This is bolded, but it's not the heading. Lanthanides or rare earths, right? These are elements from Ce to deuterium, right? Not from lanthanum, right? I told you about this before. Then it's actinides, right? Actinides are from thorium to lawrencium, right? Even in this, actinium is not included, right? Thorium to lawrencium, guys. right? So these lanthanum and actinum, these show different properties in comparison to the other elements of the actinide and the lanthanide series, although they are named after them, right? Coinage metals, we've talked about them, they are in the same group: copper, silver, and gold. Very important, right? Noble metals, right? Very low reactivity, right? These are very important again. Noble metals, you should remember, because they are called noble because they are very, very less reactive, right? So, gold, silver, gold, platinum, and mercury, right? So they, because they have very, very low reactivity, they are used for many, many purposes. For example, even gold is still stored in your home, right? Because it's very, very less reactive, so it can survive, right? So gold has been a currency for a very, very long time for this very reason, right? Now it's not, right? Gold standard was removed, right? But still, people store gold, right? In hopes for future, for the gold prices to rise, right? So they are traded and everything. All right. So then there are trans uranium elements, elements beyond uranium 92, right? 92 is the atomic number of uranium, I told you, right? Radioactive element uranium, right? After that, all the metals are called trans uranium metals, right? Then the bridging elements, which are the elements of the third period, guys, right? This is important. The bridging elements are the elements of the third period, right? Then there is a diagonal relationship, right? For example, between lithium and magnesium, beryllium and aluminium, and boron and silicon, right? Which, though they are placed in different groups, show some similarities in their properties. So if I just go back, right? So it says lithium and magnesium, right? For example, over here. Then beryllium and aluminium again show a diagonal relationship, right? Then boron and silicon, right? So although, guys, so this right, beryllium, aluminium, boron, silicon, they show a diagonal relationship. Their properties show a strong correlation, although they are not placed in the same group, right? I hope you have understood this, guys. We'll talk about the diagonal relationship and why is it shown in detail, right? Not now, right? The coming lectures we'll do that, right? Next up, guys, so this is what we've seen over here. So 1s, the 1s gets filled first, then 2s, 3s, 4s, 5s, 6s, 7s, right? Now after that, guys, what happens is after 2s, right, the 2p will be getting filled, because we've talked about this, right? Ns gets is the lowest energy. Then I'm talking about energy, right? Again, so ns, then n minus 2f, right? N minus 2f, not nf. N minus 2f is what gets filled after ns, right? If there is a f orbital available, right? For everything there is not an f orbital available. For example, there is no 3f orbital available, right? Till 3f there is no f orbital available, right? So n minus 2f. Then what we have is n minus 1d, right? Not nd, n minus 1d, and then np, right? I hope you've understood this, guys. So 2s will get filled over here first, then 2p will get filled over here. Over here it's 1s and 1s that is getting filled, right? Over here 3s will get filled, and then there is no 3d that will get filled, right? Because n minus 1d gets filled, right? Because there is not an f orbital available, next thing it will look at is a d orbital and not nd, n minus 1d. But n minus 1, that is 2d, is not available, so that's why the 3p group, the np, the 3p after 3s will get filled. If you're talking about 4s, then it will, there is no f orbital available in the n minus 2th shell, which is the second shell. So the 3d will get filled, and then 4p, right? Np, 4p, right? We're talking about 5s. Again, there is no f orbital available in the third shell. So again, we'll go ahead and we'll find n minus 1d, which is 4d, right? And then np, which is 5p, right? Similarly, if we move to 6s, right? 6s, then the lanthanoid, this will get filled, right? The 4f orbitals will get filled. These are called lanthanoids and actinoids, right? If they are, so, or the inner transition elements, right? The f block elements. These are the f block elements. So after 6s, 4f gets filled. Once the 4f gets filled, then 5d again will get starting getting filled, right? And then because 6s, ns is 6s, then n minus 2f will be 4f. In the fourth orbital, the fourth shell, there is a fourth F subshell available, right? F subshell available, then it will be 5D that will get filled, and then there will be 6P, right? So no sooner does it cross this 4F, right? When this 4F gets filled completely, again 5D starts getting filled, so it again comes into the transition elements, right? Transition elements are the D block elements. Remember? Right. Then after that it again becomes 6P, right? So again it comes in the P block. Similarly over here in case of actinoids, guys. Right? I hope you've remembered this, guys. Right? Please remember the order in which the energies are there of the various subshells, right? So NS has the lowest energy, then N minus 2F, but you have to see whether it's available for a particular N minus 2th shell, right? Then N minus 1D, again you have to see whether D orbital is available for the N minus 1 shell, right? Then NP, right? I hope you've understood this, guys. Mosley, guys, if we talk about Mosley, what he did was he bombarded high speed electrons, right? High speed electrons, guys, on different metal surfaces, and they and he obtained, right, not aimed, he obtained X-rays, right? He observed regularities in the characteristics of X-ray spectra of elements, right? So guys, basically what he found out was, right, so what Mendeleev did, right, when he plotted frequency with respect to the atomic masses, right, what Mendeleev did was he plotted atomic masses with respect to their frequency, right, the frequency of X-rays that were obtained, right, when they were bombarded with electrons, right? So what he did, so nu is the frequency, right? Nu did not show such a strong correlation. More of a correlation was shown by root nu, right? So for Mendeleev, this, let's say this graph is for Mendeleev, right? So let's place atomic mass over here, right, and root of nu over here, right? So he plotted, right, atomic masses with root nu, right? Although it sort of showed a increasing pattern, right? In case of Mosley, when he talked about atomic numbers, right, and he did this, he obtained through a lot of experimentation, right? Root nu with respect to atomic numbers, this linear relation was more closely followed, right, when you were talking about atomic numbers, right, then when you are talking about atomic masses. That's when he realized, that it's better to define or characterize the elements in terms of their atomic numbers than in terms of their atomic masses, guys, right? In fact, what he discovered was that root nu, right, the root of frequency, right, nu is frequency, guys. I'll just say nu is frequency, right? This is a symbol for frequency you might have seen before. The root nu, it actually varied with atomic number in a very linear pattern, right? A z minus b, where z is the atomic number according to Mosley, right? I hope you've understood this, guys, right? And hence he was able to conclude that atomic numbers are more suitable to characterize the elements in the periodic table, right? So Mendeleev made a huge leap, right? And Mosley took it a step forward when he said, no, atomic numbers, I've obtained this by experimentation, and atomic numbers show a stronger linear correlation, right? I hope you've understood this, guys. So then modern periodic law came forth, which was given by Mosley, which said that physical and chemical properties of elements are periodic functions of their atomic numbers, right? If elements are arranged in order of their increasing atomic numbers, right, after a regular interval, elements with similar properties are repeated, right? So this is what Mosley said, and we've talked about, arrangement of atomic by atomic number in detail, just that this was said by Mosley and this is what he said, right? I hope you've understood this, guys, right? And he said that periodicity is the repetition of properties of elements after regular intervals, right? And why are they repeated, right? if you go across a group or down a period, right? If you go down a period, the properties are repeated. And why it's repeated? Because the same valence shell electron configuration is obtained, right? The same, for example, if you were talking about copper, uh, silver and gold, right? It was, if you remember, 4s2 3d1, right? Then it was 5s2 4d1, right? 6s2 5d1, right? These copper, gold, right? Copper, silver, gold, right? They were going down the group. So because the electron, the last shell, the valence shell configuration is the same, they show the same properties, right? Okay, down the group, right? I hope you've understood this, guys. So periods and groups are again what was used in the modern periodic table as Mendeleev used earlier, right? But they were atomic number that was used, right? And we've been talking about atomic number itself in the previous slides, not atomic masses, right? We've been talking about electronic configurations and everything, which of course, right? You already know it's based on atomic numbers, right? The number of electrons, right? I hope you've understood this, guys. So periodicity is important. The repetition of properties of elements at regular intervals when they are arranged in order of increasing atomic number, right? So quantum mechanics and periodicity are related. So Aufbau principle, right? Aufbau principle and everything you must have studied, right? So if we're talking, for example, about alkali metals, right? So when an alkali metal, right, it reacts with water, right? What it forms is a hydroxide, right? The metal hydroxide, MOH, alkali metal hydroxide. So it will be MOH itself, and H2 will be obtained, right? If we're talking about lithium hydroxide is not very stable, but sodium hydroxide, potassium hydroxide, right? Then rubidium, francium, and cesium, right? Everything, right? So these are alkali metals. They react in particular order, right? So the relation between quantum mechanics and periodicity is very, very simple. It's that in the orbitals are filled in the increasing order of their energies, right, which was stated by in the quantum theory by of Bau, right? And we know that because of this, the filling of the valence shell electrons is why we obtain periodicity, right? So that's the relation between quantum mechanics and periodicity. I hope you've understood this, right? Now we've talked about this 3-4 times now, right? This is the order in which it gets filled, right? The first group, it does not have any 2p, right? The first, so hydrogen and helium, right? Although helium is placed in the p block, it does not, I mean, it's placed in the cornermost because it's a noble gas, right? Helium, but it does not show, it does not have a p orbital that's filled, right? But still it's placed over here, but so no problem, right? Then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, right? We've talked about this, and I'll write it down again. The energy, increasing order of energy is basically ns, n minus 2f, right? Then it's n minus 1th p, then is it's nth p, right? And this is the same thing that has been showed over here, right? Moving on to this particular question, guys, right? How would you justify the presence of 18 elements in the fifth period of the periodic table? When we are talking about the fifth period, guys, right? So fifth period means the final orbital that's getting filled is the fifth. The final shell that has been getting filled is the fifth shell, right? That's getting filled. So in the fifth shell, the 5s, I mean, if you remember the energy again, so it was ns, then n minus 2f, right? Then n minus 1d, right? And then np, right? So first of all, what will get filled, guys? Ns, right? So ns, so 5s2 will get filled, right? So 2 electrons in the s orbital can get filled, right? So s में 2 भर सकते हैं, right? Let's remove this 2 over here. That depends, right? So s में 2 भर सकते हैं. Then there is no 3f, right? There is no 3f, n minus 2, that is 5 minus 2, 3. There is no 3f, right? So that means that this will not get filled. Then n minus 1d, right? N minus 1d will be basically 4d, right? 4d is available, right? So now 4d will get filled, right? And after that 5p will get filled, right? The maximum number of electrons that any s orbitals can do is 2. any d orbital can include is 10, and any p orbital can include is 6. So if you add them up, you'll get only 18. Right? So in the fifth period, only 18 elements can be present. Maximum, right? 18 elements are in fact present in the fifth period, right? Because maximum of 18 electrons can be included when we're talking about the fifth, right? If you're talking starting with filling with the fifth shell, right? I hope you've understood this, guys, right? So we've covered a lot today, guys. Periodic table, right? I hope I've given you a broad picture of what will follow in the next lectures, right? So a lot of exceptions will be there, right? Inorganic chemistry is nothing without exceptions. There are a lot of exceptions, right? But you must understand that there were a lot many arrangements, right? Lot many organizations were done, right? And those organizations were not perfect, right? We tried to organize it in proper way, but there were some things, right? There were many things in fact that won't fit that trend exactly, right? So those trends are explained as exceptions. There was different explanations that had to be given for them, and hence exceptions came out, right? So don't be afraid of inorganic chemistry. There is a lot to understand and there is a lot to memorize also, right? So you'll have to do both things, right? Just keep following this, right? And I'll see you in the next lecture. Thank you.